My name is Sahil Trivedi, and this is my Lab 1 on charged tapes for Physics 2212. So, getting right into it, in the introduction, we see that the purpose for this experiment is to determine the amount of charge exhibited between two pieces of tape, and this gives us a way to understand how electrons are transferred between the surfaces and their resulting charges. The key concepts to focus on throughout the entire experiment here is one, Coulomb's law, which you can see the charges exhibited in that diagram in the first part, and then the second one is Newton's second and third laws. You see Newton's second law here, figuring out the force external, and then our mass and acceleration, which is resulting in the movement of the two pieces of tape. But here it would be driven by the charges from Coulomb's law, as opposed to just simple acceleration. Taking a look at the setup, all you need to complete this is office tape, two stands, a flat surface, and a tape measure. So basically the way to do this and transfer the charges in the first place is to create a base tape, and this is simply done by taking a piece of the office tape, laying it down flat on what we used was our physics table, pressing it down with our hands, and having a place where you can rip it off. And then the second part was placing a second piece of tape on that surface of the base tape and pressing down firmly so that both pieces are perfectly on top of each other and they're pressed down as much as possible. And then we place the bottom piece of tape of our next piece on two stands a decent bit apart so there's some slack and the bottom tape could move up and down. And then lastly, we would rip off the piece of tape that was on the base tape and move it closer to the horizontally suspended piece of tape on the two stands and measure the amount it moves up with the previously mentioned tape measure. So looking at the initial conditions and assumptions, on the right you can see what I meant by using the base tape. And on the left you see that the tape mass was 2 times 10 to the negative fourth, obviously because tape is extremely light. The tape length was 0.2 meters, the area was 0.04 meters squared, and you could use that to find the width of the tape as well. The atom area was 1 times 10 to the negative 20th, obviously, and then the atoms per tape were calculated to be about 4 times 10 to the 18th. So looking at our calculations, it's laid out pretty simply in this Excel table. You can see some of our sort of initial inputs here from gravitational force, tape mass, and the electric force, which were mentioned on the previous slide. You can see the separation distance as well in the second part, and then the length and area of our atom. And then this all flows into calculating the number of electrons. So basically how this was done was we simply took those initial inputs, which you can see up here, and use that to calculate our electric charge right here. And this was done according to our obtained formula, which was the square root of our B3 times 4 times 3.14 times 8.854 times 10 to the negative 12, and then finally our B6 squared. And then the separation distance was taken, and that flows all the way down into calculating our atoms per tape, and then finally electrons per atom. And then simply our Q over E is going to give us the total number of electrons present in the atom due to the fact that E is so small. So as for assumptions, air resistance is negligible. The charge is linearized over both of the tapes, and charge is assumed to be the same, resulting in the repelling of the two pieces of tape, which is important as these 2 points especially could affect the results, but we really have no way to track that. Taking a look at our computational model, you can see that it's a very simple bit of code where we have our gravity, our KE, the mass of our tape, which was previously mentioned, and our distance between the two pieces of tape. These calculations, you can cross-reference them with the ones used here, and they're exactly the same. And this was basically used to determine our total E, which is which takes us through the charge on each tape, which you can see here, the electric force, and the gravitational force on the top tape. And here's a diagram showing the results. Now looking at potential errors, as mentioned before, air resistance and friction are technically not negligible and would result in a net loss in charge. The distribution of charges across the tape are not uniform, and this could skew results. And measuring is not exact, as the charge moves away even as the the charge from the tape comes close to the other one, which makes measuring a bit tough. And the amount of electrons from each trial could be a bit different, so many trials should be necessary to find the exact amount. Taking a look at our discussion questions, if the electrons and protons had inverse charges, this would not cause a large difference as the same repulsive or the same attractive charges would be the same. The attractive and repulsive properties would mirror the original experiment, and only the vector fields, if you were to draw them in, would be reversed. And then why is it important to handle the charged tapes as little as possible? Because continued contact with your hand could cause a tape to lose much of its charge since you are grounding it. And we want the original charge obtained by the tape to hold somewhat constant, and so touching it less would be better. Thank you very much for watching, and this is my Physics 2212 Lab 1. Thank you.